So going into chapter 3. So now this is taking and looking at the one specific type of subatomic particle that we didn't really talk about last time. So remember, you have protons, neutrons, and electrons. And so we said last time that protons and neutrons, they give the atom mass. That's really, they're the reason that you have atomic number. Those are the ones with the atomic mass. So this chapter, legit, is really all about the electrons. So remember we said that electrons are outside of the nucleus. Electrons are extremely small, 2,000 times smaller than a proton or a neutron. Atoms are constantly moving, and they exist in like an orbital. So they're in this constant motion around. So very small, negative charge, and kind of like constant motion. So this constant motion creates this orbital. Okay? So in this, here's an example. So here's an atom, right? So remember we drew the atom with the circle. Remember the nucleus is in the center of the atom. These electrons are found in very specific areas. From smaller atoms to larger atoms, as the number of electrons increases, so as the size of the atom increases, the atomic number increases, so does the number of electrons. You always have electrons will fill the lowest energy levels before they fill higher energy levels. So this one here, yep, so hold on, it just bumped me off. So electrons will all exist in these orbitals. And the rule is that no matter how many electrons an atom has, you will always find lower energy levels filled first. And the lower energy levels are really the ones closest to the nucleus. So here, this is the lowest energy level because it's closest to the nucleus. Whereas the E, the electron that I've got drawn further out, this one has higher energy. It's further from the nucleus. And a way that you can think about it in terms of energy is how fast they have to move. So can you see the electron closest to the nucleus has a shorter path to make an orbit? The one further out has to go faster in order to be able to make the same loop in the same period of time. Does that make sense to everybody? So if I have an electron and I've got to go like this, and I got to do that in like 1 second. But then this electron has to go all the way around like this in a second. Do you see that the outer one would have to be going faster to be able to make that same loop? So the further from the nucleus, the faster those electrons have to be able to move, the higher energy they're going to have. So in fact, with the two smallest of all of the elements, hydrogen and helium, so you know that those are all the way up at the very top row on the periodic table, hydrogen has 1 proton and 1 electron. So that 1 electron fits in that smallest energy level. Helium has 2 protons and 2 electrons, and its 2 electrons fit in that smallest first energy level. In fact, that first energy level is so small, you can't put but 2. So 2 electrons is the maximum number that like fits in this center. I think of it, it's so small, only 2 electrons would actually fit. So everything bigger than that, grab a periodic table because you'll definitely need that. So everything larger than that is going to have to start filling an energy level that's bigger. So we got all of these. I just need to take all these questions out. See, and then it stops. So the first energy level, so this is the one that's the lowest. This is the one that's closest to the nucleus. And here, the maximum number, not mass, the maximum number of electrons is 2. And that's hydrogen and helium. So hydrogen has 1 in that energy level, helium has 2. So then any more electrons don't fit in that first energy level. They're in the next energy level out. The next energy level out, it can hold 8. So the next one, this can hold 8 electrons. So if you look at the periodic table and you just go along by atomic number, so hydrogen's 1, that's 1 electron. Helium's 2, that's 2 electrons. So next one is we have lithium. So lithium has 3 electrons. That means that there's 2 electrons in the first energy level and 1 electron in the third, or in the second, sorry. The third electron fits in that second, because you can't put any more than 2 in the first energy level. Then going across, see beryllium's next. So beryllium's 4. So 2 fit in the first, and that means 2 are in the second. As we continue going across, we have like boron, then carbon, then nitrogen, then oxygen. So I'm just going straight across the periodic table. So boron, 2 and 3. Carbon is 2 and 4. Nitrogen is 2 and 5. Oxygen is 2 and 6. Fluorine is 2 and 7. And then we get all the way over to the far one. The last one is neon. And that one has 2 and 8. So as you go across, the number of electrons increases 1 by 1 with the atomic number. That's all that will fit in the second energy level, is 8. So then when we go to the third energy level, now we're going to have to start having a third number in there. So if we go back across to sodium, Na, only 2 electrons fit in the first, just like all the rest of them. 8 electrons fit in the second, and that's maxed out. So now I have how many in the third? 1. Right? So sodium's 11. So 2, 8, and 1 makes 11. Now, the third one can actually hold 18 as the maximum. But they found, so there's 18 electrons as the max. But what they found is that they started seeing that energy levels that created 8 electrons in the outer energy level, no matter if I'm talking about the second energy level, the third energy level, the fourth energy level, anytime I have 8 in that outer energy level, that created stability. So you can see these numbers are kind of summarized here. There's those ones that I just went through. And so here's that first energy level. And so remember, this one, the max is 2. There's the second energy level. You can see those ones. Remember, the max for this is going to be 8. But even in the third energy level, when it gets all the way up to 8, that creates stability. So here's another thing that you can see on the periodic table. So notice hydrogen, lithium, and sodium. They all have what? What do they have in common? They have hydrogen, lithium, sodium. They all have 1 electron in their outer energy level. In fact, by the flip, if we take and we look at beryllium, and on the next page, magnesium and calcium, what do you see about them? So there's magnesium. So magnesium's got 2 in the third energy level. Calcium has 2 in the fourth energy level. Beryllium has 2 in the second energy level. So they all have the same. So beryllium, magnesium, and calcium. This outer energy level is the one that they found is responsible for forming chemical bonds. So the ones we work with the most is through calcium, right? 1 through 20. So those are elements 1 through 20. They're all still part of what they call the main group. It's the first 2 columns and the last 6 columns. So in those, what they found, the number of electrons in the outermost energy level, they call them valence electrons. So if we look at like sodium, so sodium, we said it's 2 electrons, 8 electrons, 1 electron. The first energy level is full, it's stable. The second energy level is full, it's stable. It's that third energy level that's not full. So it's this electron. It's not full, it doesn't have 8. Having just 1 creates a very reactive atom. So they called those outer electrons valence electrons. So they talk about the valence numbers. But you can actually tell how many valence electrons a main group element has just by the number in front of the capital A at the top of the columns. So if you look on your periodic table, look at the capital A at the top of the first column, and you see it's group 1A. So that group here, this tells you that you have 1 valence electron. So group 2A has 2. So there's 2 electrons in their outermost shell, or 2 valence electrons. So this, you don't have to memorize this. Again, it's just a matter of remembering to use the periodic table. You don't have to, I'm not going to ask you like an electron configuration. I don't know if you ever did that in high school. I don't care about that. Okay? Because we're just using this as a way of explaining bonding. So the big players in this are not the electrons in the lower levels, it's the electron in the outer, or the valence electron. If any element doesn't have a valence electron that is number that is stable, then it's going to be reactive. So they found that if you only have 1, that's not stable. If you only have 2, unless you're helium. If you are beryllium, magnesium, or calcium, then that's not stable, including boron, carbon, nitrogen, oxygen, fluorine, all of those not stable. The one, though, that they found is stable is group 8A. And do you remember what their generic name is? They're called the... Nope. What is that last column called? They're the noble gases. They're the noble gases because they're extremely stable. They don't form compounds. Well, the really big ones, like xenon, you can force it to make compounds, and radon you can, but it's because they're so big. But helium, neon, argon, krypton, they don't form compounds. They exist as stable, inert atoms. So they found that that was a criteria. So like if you buy a can of helium to put in balloons, if it's pure helium, they exist as helium atoms. They don't exist as a compound. So they do not react with anything else. They're extremely stable. And this is because they have a stable number of valence electrons. The electrons in the outermost energy level are stable. And in fact, all other atoms react to try and be like a noble gas. So all atoms try to react so that they achieve this valence number. They call it the octet, or the stable 8. So one way of trying to define or illustrate the number of valence electrons is they use what's called Lewis dots. So the Lewis dot, you always put the symbol, whatever its symbol is, in the center, and then you put one dot to represent each valence electron. You could have a maximum of 8, right? Because that's what the noble gases have. So maximum, you would put 2 above, 2 below, 2 to the left, and 2 to the right. And so you would just like sort of spread them out around whatever the symbol is. So you could have this. So that would be the most stable. If you had a symbol, so if you looked at neon, neon would have 8 dots around it. You only ever put like 2 on a side to give up to the 8. So like hydrogen. Hydrogen has how many? Just 1, right? So you put 1 dot. And it wouldn't matter where you put the dot. You could put the dot on the left, you could put the dot on the right, above or below. It really doesn't matter, just so long as there's 1 dot somewhere around that symbol. But then what do you know then about lithium, sodium, and potassium? They're all going to have 1 dot too, right? Because they're all in group 1. So since they're all in that first column, they get 1 dot. Beryllium, magnesium, and calcium, they get 2. And it, again, if you wrote it like this, that would be fine, okay? Just so long as there's 2, because those are the valence electrons. Remember the number above the column tells you how many. So you don't have to memorize it. You just have to remember to look at the number in front of the capital A. So boron and aluminum, they would have 3. And you could write them like this, or you could spread them out. Okay? Mm-hmm. You see the dots now? Do I need to change my colors? My one pen's acting wonky. Let's see. Nope. So IT's supposed to come tomorrow and check this. I was like, I need you to come and sit in my class at like 9:30 because that's usually when it starts. And then I need you to sit here and watch until it starts happening because they're like, well, we don't know how to troubleshoot. And I'm like, well, you need to come sit in my class. And they were like, well, we don't want to be a distraction. I'm like, you won't, I swear. This makes me really angry. And my old tablet, they swapped out my laptop, and the old one didn't do this near as bad as this one is doing. So I'm trying to get them to give me my old one back. So if I was going to do now, carbon and silicon, when you have more than 3, now you try to spread them out. So with these, carbon, routinely, you go 1, 2, 3, 4. Put 1 dot, 1 above, 1 to the left, 1 to the right, 1 below. And I always learned, the way that we learned the classical way is if you took the symbol, you always started, put a dot above, and you went around clockwise. 1 above, 1 to the right, 1 below, 1 to the left. Same thing then would happen with silicon. Now when I go to nitrogen, though, nitrogen has, so now 1 pair is going to get doubled up. So you'd usually start at the top, go 1, 2, 3, 4, and then double pair off the top ones. And it doesn't matter. So if you wrote it like this, I am not like that. If you wrote it like this, I would not mark it wrong, okay? The key thing is you should have 3 singles and 1 pair to display the total of 5. Oxygen is going to end up having how many dot pairs? So, well, you could do it that way, but remember, if you've got carbon or higher, you always want to make sure you have them singled out. So I go 1, 2, 3, 4, but then I'd have 5, 6. Okay, so there should be 2 paired and 2 singlets. You don't want to have a side empty, okay? And so it would be fine if you had them like this. That would be okay too, but just make sure that you spread them out. Fluorine and chlorine, bromine and iodine, what are they going to look like? They're all going to have 7. So that's a lot of dots. And again, you could put your single dot anywhere you want. Just make sure there you've got 3 pairs and then 1 single. 3 sides are going to have 2 electrons. 1 side is going to have a single one. So you don't have to memorize these. You just have to remember, put yourself a note, you know the number of valence electrons by looking at the number in front of the capital A. We call them Lewis dots. So when we get to helium, what does helium have? How many dots? Nope. Helium would have, nope, doesn't have 8. This is like the exception to the rule. It has 2. Look at your periodic table. So do you see that helium has 2? How many electrons fit in the first energy level? Only 2, right? Remember when we were doing them and listing? The first energy level is really close to the nucleus and only 2 electrons fit. So 2 electrons max in the first energy level. That is why helium would only have a 2. But neon, what would it have? 8. Argon, 8. All the other ones, 8. But helium, just remember, because the first energy level only has 2, it's stable with 2 because it fills that first energy level. But all other atoms, they want to try and have 8. Helium and hydrogen only want 2. So hydrogen is going to kind of follow what helium tries to do. So hydrogen's not going to try and get 8. Hydrogen's going to end up trying to just get 1. So 1 would make that first energy level stable. Okay, so all of this is really based on this reactivity that they found is really based on these lack of full outer energy levels. See, and again, already. It's coming. Right? So then here's some just randomly listed. So use your periodic table and figure out how many dots does each one get. All right, so what'd you get for sodium? 1. How about nitrogen? 5. I'm just going across. Hydrogen? 1. Magnesium? 2. Argon? 8. Sulfur? Nope. How many? 6. So remember it's in group 6A. Aluminum? 3. Chlorine? 7. Carbon? Oxygen? 6. Remember I said it wouldn't matter, like just make sure that you spread them out. And then fluorine. And the last one is phosphorus. 5. Okay, so just remember it's just based on the group number at the top of the column. Just make sure that you spread them out. All right, everybody got those? So what they found was that atoms that didn't have 8, except for hydrogen and helium, for atoms that didn't have 8, they're reactive. 8 creates a very stable atom. So any atoms that don't have 8 react to form compounds. Some atoms are going to give away electrons. Some atoms are going to take electrons. Some atoms actually share electrons. So there is this interaction that occurs with the valence electrons between 2 different atoms. That's going to create a bond, and that's going to give both of those atoms 8. So it's going to create, always keep in mind, well, 8 is the stable, except for hydrogen and helium. 8 is the stable. There's always an exception in life. They're the exception, okay? So that's the goal. So here's how the first one works. So I think it's, so in this, I'll zoom in a little, maybe. So if you have an atom of chlorine, just an atom of chlorine, okay? So chlorine doesn't even exist in nature as a single atom. It exists as Cl2. It'll already exist as a molecule. An atom of chlorine has 17 protons and 17 electrons, right? Its atomic number is 17. 17 protons, 17 electrons. It's in group 7, so we know that it has 7 valence electrons. Chlorine is so reactive that if you inhaled this, it would react with the water in your lungs and cause severe damage. So this is why, like, you don't inhale chlorine gas, okay? Extremely reactive and would be toxic if you inhaled it. But this is all because of chlorine having that 17 electrons. That valence number of 7 makes it very stable. Very reactive. So if I have chlorine, remember that I have 1, 2, 3, 4, 5, 6, 7. I have 17 protons total, 17 electrons in an atom. That's very unstable. So what would make it more stable is if that chlorine could just gain 1 electron. If this chlorine can gain just 1 electron, now what would it have? How many electrons would that give it? Now it would be 1, 2, 3, 4, 5, 6, 7. But if it could gain just 1, now it would have 8. So if an electron could get added to it, now how many protons would it have? Still has 17 protons. That hasn't changed. But how many electrons does it have now? 18. Remember that protons are positively charged, electrons are negatively charged. So it has 1 more negative electron than positive proton. So the charge of this chlorine atom is now a negative charge because it has 1 more negative electron. But now, see, its valence electron is 8. This is an ion. Ions are atoms with unequal numbers of protons and electrons. So they have unequal protons and electrons. So when you look at a normal atom, they're equal, they're neutral. But when you make an ion, the atom is going to either give up or take an electron on to create the stable octet. And in fact, this is a very stable ion. This is floating in your blood right now, right? Chloride ions. So remember that chlorine is one of the 7 of the minor elements, and it doesn't exist as a chlorine atom. It exists as a chloride ion. So they call it the chloride ion. So where does this electron come from? So this electron comes from the next slide, which is sodium. So I'm going to blow this one up. So in this, sodium, as an atom, you see that it has 11 protons and 11 electrons. And if you did its valence Lewis dot structure, how many dots would you put around it? Just 1. So remember with that, it's just going to have 1. So Na, you'd only have 1 dot. So that is about as far from 8 as you can get. In fact, sodium metal, you can actually isolate and extract sodium metal. Sodium metal reacts with the air. Sodium metal reacts explosively with water. If you took a chunk of sodium metal and you threw it in water, it would react so vigorously with the water, it would boil it. So like you would actually get like this steam and it would like almost like bounce across the top of the water. It would react so vigorously, lots of heat. So if you have sodium metal, you can't just leave it on the shelf. You actually have to store it under kerosene. You have to keep it away from air. You have to keep it away from water. So we don't have any in the lab. Okay, because like that's all I need. Something like that is there. Okay, seriously reactive because it needs 8 How many does it have? Only one. So what is it trying to do? This with 11 protons and 11 electrons. If sodium can lose one electron, now you'll have a sodium ion and it'll still have its 11 protons, but now how many electrons will it have? 10. So what other element has 10 electrons? Which one has an atomic number of 10? So now it makes it like neon. So it will actually give it a noble gas configuration. Neon has 10 electrons. So if sodium can lose that outer electron, that's going to make it like a noble gas and give it the stable octet. So it lost the 1, but the next level in has 8. So the next level in becomes its outer shell, and now it'll have that stable octet. But while you call sodium a sodium atom, the one that has that 1 valence electron, if it loses its valence electron, now it has 11 protons and 10 electrons. What's the charge on that? It has 11 positives and only 10 negatives. It's going to be a plus. It has 1 more proton than electron, so it's going to have a positive charge. So this is also an ion. Positive ions are the cations, negative ions are the anions. And this is one of the primary ions that you find floating in your blood, right? So you don't see sodium metal in your body, you have sodium ions, which form very stable ions that can exist. They don't react with water, they just help in fluid balancing primarily in the blood. So this is a very stable octet that is left behind once it loses that outer electron. And remember that sodium is also one of those minor elements, one of the big 7. So if we put these two together, if you start off with a sodium atom and a chlorine atom, see that the sodium has 1, chlorine has 7. If the sodium transfers its electron to the chlorine, the sodium becomes positively charged, the chlorine becomes negatively charged. So this is our positive and this is our negative. So what do you know about opposites? What do you know about positive and negative charges? They attract. And this is an ionic bond. So the attraction between oppositely charged ions is an ionic bond. So it's kind of interesting, like you think of something that's extremely reactive, sodium metal, very reactive, chlorine atoms, very reactive. When you mix these two together, you end up with a sodium ion and a chlorine ion or chloride ion. And this, what do you do with this? This is commonly called table salt, right? NaCl. So it makes something that's very stable. Transferring these electrons creates a really stable compound. In fact, in order to melt sodium chloride, you have to heat it to about just over 2,000 degrees, about 2,300 degrees to get it to melt. That's how stable it is as a crystal, as a solid. So a couple things to take away. One, do you notice that the metal is always written first? The metal 1 is going to lose electrons and it's going to end up with a positive charge. The metal is always written first in a formula. And when I name this, I call this sodium chloride. I always use the whole name of the metal. So what's different about the nonmetal? So chlorine is our good example of a nonmetal. It's always written second or written afterwards. Non-metals always what? What happens to them in terms of their electron numbers? The chlorine to the chloride ion. Gains. So these gain electrons. They always become negatively charged. They're always written second. Like you've never seen ClNa. It's always NaCl. So the metal's always written first, then the non-metal. And then the chlorine doesn't stay chlorine. When they use it in forming a compound, it changes to chloride, okay? So you use the first part of the nonmetal and add IDE. So if we look at those nonmetals, so what will fluorine become? Fluoride. Right? So you don't brush your teeth with fluorine, you brush your teeth with a fluoride toothpaste, which means it's some kind of ionic compound. What would you say bromine becomes? Bromide. First part of the nonmetal, and then add IDE. Iodine? Iodide. What about oxygen? It is oxide. So it's just the OX and then IDE. What about nitrogen? Nitride. It's the NITR. It's kind of like the first part of the nonmetal plus IDE. The metal, you just say the name. So it's just sodium or lithium or potassium or calcium. You always use the whole name of the metal. You just use the first part of the nonmetal plus IDE. Okay, so let's practice some of them. So here's some steps. So this is the next one. In steps, you might be given a metal and a non-metal and have to write the formula. You might be given the name and have to figure out the formula. You might be given the formula and have to figure out the name. You can do all of those, okay? Just so long as that you recognize and follow the same steps with each. So first, always make sure you list the metal first, then the non-metal. No matter what, metal always gets listed first. You always have to assign a charge. Now for us, when we did sodium and chlorine, sodium, if you look at group 1, remember sodium loses 1 electron? So all of the group 1s are all going to lose their 1 electron. So lithium, sodium, and potassium, everything in group 1 will always become a +1 charge. Right? Because they're all in group 1. So what's going to happen with the ones in group 2, like beryllium, magnesium, and calcium? What are they going to do? They're metals, so they always lose their valence electrons. They're going to lose both of their valence electrons, so what would their charge be? So if I have, Be, Mg, and Ca, that's group 2. They're going to lose those 2 valence electrons, so they will be positively charged a +2. Beryllium, magnesium, and calcium. Those will always end up with a +2 charge. So the group number that tells you the number of valence electrons also tells you the charge on the metal. And really, the only other metal that we talk about this way is aluminum. So what do you think the charge on aluminum will be? It's plus, because all metals end up positive. This will be +3, because it's in group 3. It's going to lose its valence electrons. Metals will lose their valence electron, and that group number, they're always going to end up being cations, positively charged. So nonmetals are always going to gain, right? So if they gain electrons, then they're going to be negatively charged because electrons are negatively charged. So we said chlorine has what charge? Chlorine was a negative, right? So the way you figure out its charge, 8, the number that makes it stable, the stable 8, minus their group number tells you their negative charge. Right? So remember that these are the negatives. So chlorine is going to be negative. It's going to gain 1 negative electron, giving it a negative charge. So then what do you know about fluorine, bromine, and iodine? They're also, look on the periodic table, see where chlorine is, they're in the same column. So they've also got 7 valence electrons. They're also going to gain 1, so they're all going to have a -1 charge. Right? So if you have 7, you're going to gain a negative electron to make 8 and be stable. So then what about oxygen and sulfur? Oxygen and sulfur are in group 6. So they're going to gain 2 electrons to become stable. So what will their charge be? Yep, a -2. So if you take 8 and subtract their group number, which is 6, that'll tell you their negative charge. So metals are always going to end up positive charge. Non-metals are always going to end up negative. So really the last one, N and P. Nitrogen and phosphorus, what would their charge be? So find them on the periodic table. 8 minus their group number means they'll have a -3. And those are pretty much, these are the primary ones. Okay? So we've got the metals in the first 2 columns and aluminum. We've got the non-metal groups that I've got listed. The chlorine, fluorine, bromine, iodine, that's group 7. Group 6 is oxygen and sulfur, and group 5 is nitrogen and phosphorus. Those are pretty much the groups that do this ionic combining. Now when we did Na, it was positive, Cl negative. Do you see that it's like 1 and 1? There's Na's +1, Cl's -1. Do you see that NaCl as a whole would be a neutral molecule? There's a +1 charge and a -1 charge. Do you see that those balance? Okay. Ionic compounds have to be neutral as a whole. So the total number of positive ions and negative ions have to equal each other. So you do that by figuring out the formula. So in this example, see magnesium. Magnesium's over in group 2, so magnesium has a +2 charge. Chlorine has a -1 charge. So see, they're not the same. So do you see the positive and negative charges are not the same? So the way that you get them to be the same is you determine the formula. You take the number for the charge on the magnesium, and that tells you how many chlorines. The number for the charge on the chlorine tells you how many magnesiums. So what I always say is you just swap them. So this 2 goes here, this 1 goes here. So the charge for the metal tells you how many non-metal. The charge for the non-metal tells you how many metal. So you're going to start off, you assign the charges, and then you just swap them. And the reason you do this, so magnesium, remembers the +2, chlorine's a negative. Do you see that that molecule is neutral? I have 1 +2 magnesium, but 2 -1 chlorines. So they're going to balance each other out. So they have no overall charge. 1 +2 magnesium and 2 -1 chlorines. And so together, they're going to make a neutral atom. So what if I had lithium and oxygen? So what would the charge on lithium be? Look at your periodic table. Figure out what group is it in. So it's going to be a +1 because it's over in group 1. What would the charge on the oxygen be? -2. So see, they're not the same. So what would the formula end up being? Metal goes first, then the non-metal. How many lithium? 2. Oxygen, just 1. But remember, if there's 1, you just leave it, right? Like H2O, you don't put a 1 after the O. So if there's only 1, you just leave it. So see where I got that. So in doing this, I took this 2, tells me how many lithium. the charge on the oxygen tells how many lithium there are. The charge on the lithium tells me how many oxygen. So this last one, number 4. Number 4 says, well, what if you have two that have the same charge? Like if I have calcium and oxygen, if you look at calcium, it's in group 2, so it's a +2. And I look at oxygen, it's in group 6, so that's a -2. So they have the same. So notice here and here, they're exactly the same. So if I swapped those, I would end up with Ca2O2. The rules say is you always want the simplest whole number ratio. So this doesn't happen very often, but this would be an example where I would want to make sure that I simplified the ratio of calcium and oxygen in CaO. So since calcium's a +2, oxygen's a -2, I can simplify the ratio to just CaO. And then the last one is you just make sure that you use the whole name of the metal when you say it. Second word is the first part of the nonmetal plus IDE. So that is where you come up with sodium chloride. MgCl2 would be magnesium chloride, and CaO would be calcium oxide. Whole name of the metal, first part of the nonmetal, and the IDE. So let's practice, not those ones. I had some easier ones. Where are you? Really? I had some easier ones. I don't know. I might have deleted that slide. I tried to simplify some of my slides, and maybe I pulled too many of my slides out. Okay? So let's have a blank. Okay? So in these, give me the name or the formula for these ionic compounds. So if I want you to combine sodium and bromine. So combine sodium and bromine. So you just have to add this underneath. So just sort of some practice of ones. Okay? So for that one, I want you to tell me the correct formula. See, here's the formula. And then I want tell me the name. So if you were going to combine sodium and bromine, what would the charge on the sodium be? +1. What would be the charge on the bromine? -1. So if I swap these, they're equal. So the formula would just be NaBr. And what would you call it? Sodium bromide. Whole name of the metal, first part of the nonmetal plus IDE. What if I was going to do this one, give the formula of potassium oxide? So what I've got to do with that is I've got to take the name. So potassium is a what? What's it stand for? Potassium is K. And oxide is O. What is the charge on potassium? +1. See, it's in group 1. So potassium's a +1. Oxygen would be a -2. Does everybody know where you got that? Potassium's in the first column, and metals are always positive by their group number. Oxygen's in the 6th column, so 8 minus 6 tells you the negative number. Right? So remember, that one's, I always think, like how many to make 8. It's going to gain electrons to make 8. So 8 minus 6 tells you the negative. Now I got to swap these. So what's the formula? K2O. Right? The charge on the oxygen tells me there's 2 potassiums. The one on the potassium means there's just 1 oxygen. Right? So I just take and swap them. So if one's just a plus, then you know that's a +1. And you don't have to write the 1. Okay? Try the other ones. Follow the same steps. Okay, so let's try the other one. So how did you do Al and S? So Al, the charge, plus 3. So find aluminum. It's over in group 3A. So that's how I know the charge. Sulfur, 8 minus its group number means that it's going to be -2. So they're not the same. So I've got to swap them. So how many aluminum? 2. And how many sulfur? 3. And then I'd call this what? Yeah, aluminum sulfide. Whole name of the metal, first part of the nonmetal plus IDE. Magnesium, what's the charge on magnesium? +2. Charge on the nitrogen, 8 minus its group number, so it's a -3. So again, I got to swap them. So now this time magnesium ends up with a 3. Nitrogen ends up with 2. Okay, charge on the metal, just swap from the charges, you just swap them and that tells you what the formula is. And then this one's name? Magnesium, what? Nitride. Okay, so they call these binary ionic compounds because they're just 2 elements, and they're always going to be this way. Metal and a non-metal, assign the charges, swap them if you're trying to find the formula. If you're saying the name, whole name of the metal, first part of the non-metal plus IDE. So lithium, what is lithium? Li, and its charge is +1. Phosphide would be phosphorus, which is P. 8 minus its group number would be -3. So they're not the same. I got to swap them. So that means how many lithium and how many phosphorus? Yep. To be Li3P. So last one, calcium formula. Ca, and its charge +2. And then iodide is, what's the symbol for iodide? Just an I, because it's an iodine, right? So, and its charge would be -1, right? See, it's in group 7. So 8 minus 7 tells you the negative number. So remember that the non-metal is always negative, the metal is always positive. So your first element's always the metal, it's always positively charged. Second element's the non-metal is negative. Now these are not exactly the same, so I got to swap these 2. So I would end up with Ca 1, and I would be 2. CaI2. Calcium iodide. Right. Remember the zigzag. And this is another way. So if I just gave you if I asked you calcium iodide, is this an ionic compound? If you look on the periodic table, calcium's a metal, iodine's is the non-metal. They're on opposite sides of the zigzag line, then you say yes. Okay? So that's a way to tell an ionic compound, is that they're going to exist with elements that are on opposite sides of that zigzag line. These are your non-metals, these are your metals. All right.
So with B, meaning boron, how got it's in the third.
Yeah, so now boron is not really, it's almost like a metalloid. So boron is not, so I really kind of went through, it's all of those first 2 in the first 2 columns, not hydrogen though, because that's not That's the weird one. It likes to be like a non-metal. But lithium, beryllium, sodium, magnesium, calcium, and potassium. Those, and then aluminum. So really it's only those 7. Those are really the only 7s. So we went through here. So it's really, if you're looking through and you're like, oh, which one's for sure? It's pretty much those are the 7. The first 2 columns and aluminum. And then for the non-metals, it's group 7, those 4, plus oxygen and sulfur and nitrogen and phosphorus. So see, it's really, these are the non-metals. So it's combinations of those. Okay, so even though you're like, look at the periodic table, you're like, there's so many. Well, we don't really, there's a whole bunch of them that we don't really use. Because remember, we talked about how there's only 27 elements in the body, even though there's 118 known. We don't come in contact with the vast majority of them. And so we're really looking at ones that have more of an application to us, to the living systems. Okay? So here's just another way of remembering, like when you do this swapping, like aluminum's a +3, oxygen's a -2. And notice like the book likes to say 2 minus, 2 minus, -2, same thing. Okay? So I don't care if you write 3 plus or +3, I really don't. Because I'm really bad about putting my charge before my number. But the book is gonna put the number before the charge. It doesn't matter though, okay? Either one's fine, perfectly fine. And I don't think any of your math, if you have a mastering it and you had to put in a charge, put the number first or they might squawk at you. So instead of a +3, put 3 plus. Okay, see how their subscripts are a little different? Again, it's just like the strict part of it. But notice in this, if aluminum's a +3, oxygen's a -2, you just take those charges, swap them, and that tells you the formula. And that formula now is going to give you a neutral ionic compound. But I can identify that that's ionic because aluminum is a metal. Okay? Ionic compounds will always have a metal first. So there's 2 weird ones, 2 weird groups that exist, and that's the only thing I want to try and like introduce, and we'll practice them next time. So the first one is those strange transition metals. Those are the metals that have the capital B, the 3rd column all the way over to the 13th column. So they're not the ones on this end, they're this group that's like in the middle, okay? Transition metals can actually have different charges. They can lose, like iron. Iron can lose 2 electrons and be stable, but it can also lose 3. And it all has to do because they're big. They're relatively big, like looking at iron, that's 26 electrons. So it has a larger than normal, than the small ones that we talked about. It has a larger number of electrons, and so it can actually exist stably in more than one form. But there are only 3, out of all those transition metals, there are only 3 that you need to know. Okay? And again, these are the 3 where you have to know their symbols anyways, symbols and elements. Remember I gave you that back in chapter 1. So iron, which is Fe. So you see iron is 26, chromium, which is number 24, Cr, and copper. Copper is Cu, number 29. So what's interesting is like iron can be stable as a +2 ion or +3. It can lose 2 electrons or 3 electrons and be stable. So that means I can have an iron ion combined with chlorine in 2 different ways. So see in this one, this is iron +2. The chlorine's always a -1. But you see how that swap occurred? How the iron being a +2, the chlorine having that -1? Or I could have FeCl3. So in this one, the iron's a +3. The chlorine's still a -1. It just doesn't. So it's stable, like when you get these bigger orbitals, because remember how we said like the first one's only 2, second one's only 8, third one is 18. Well, this is actually going into the 4th. So when you get up into those, they're really moving fast and the orbitals are really close together because they're so big. Like you think like this orbital, the first one's real small. So only 2 fit there. When we get to one out here, now we have 18 electrons going in all these different orbital paths, and they're very close in energy. And that's why losing 2 can make them stable, losing 3 can make them stable. So like chromium can do a 2 or a 3. It can be a +2 or a +3. Copper exists as a +1 or a +2. But since these exist in both ways, you actually have to indicate their charge when saying their name. Because can you see this is iron chloride and this is iron chloride? Because they're both FeCls. So they both would be iron chloride, but since this one has a +2 charge, you would call this iron 2 chloride. And you can use the parentheses or not use the parentheses, it doesn't matter to me. But you use that Roman numeral to indicate the charge on the iron. This one then is iron 3. So with IC, if I had a name like this, iron 3 oxide, how would I write its formula? What would you write first? Fe, and it would be a +3. So that Roman numeral tells me the charge on the iron. The oxygen, I know the charge. What's the charge on oxygen? -2. Okay? So you'd write the metal. You know the charge on that metal, and it's only these three, iron, chromium, and copper. You list the nonmetal. You know the charge based on the periodic table. 8 minus its group number is the negative charge. Now I just swap them. So this formula would be Fe2O3. So when you use with iron, chromium, and copper in their name, you have to have a Roman numeral. The Roman numeral for iron is either a 2 or a 3. Chromium is either a 2 or a 3. Copper is either a 1 or a 2. And if you look at, see, it won't go for it again. There it goes. There's a chart here. And this, like, I'm not going to ask you to learn those because those are not the names and the symbols you had to know. So cesium, barium, francium, and radium, you don't have to worry about those, right? You've got all these. You don't have to do selenium because that wasn't one that you had to know the name and symbol for. All the ones I'm asking you to learn are all ones you already have to know names and symbols for. So there's chromium, iron, and copper. So don't worry about zinc, cadmium, silver, gold, tin, lead. You don't have to worry about any of those. So these are really the ones. So these are the atoms that form ions and what their charge is. So this is sort of a chart that you can use as practicing. But really remember with the main group, the positive, the metals, they're always going to lose whatever their group number is. So see how lithium, sodium, and potassium, they all end up +1. Magnesium and calcium always end up with +2. Beryllium should be in here. So this is like, write it the way they write it. It should be a 2+. +2 is how I always write it. Okay, and then over on the non-metal side, nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine, bromine, iodine, those non-metals, it's always 8 minus their group number. And they're always a negative charge. So see the yellow group, they're all negative. Those that are in the blue, always positive. Except for hydrogen because it's the oddball, right? All right, so we'll do some more practicing with those ones. And then we're going to talk about polyatomic ions. So it's the second weird group of ions that are formed. And then from there, we can go on to covalent molecules on Monday. Okay, so we got to talk about, like, we'll practice a couple of, like, writing the formulas, giving the name, sort of like what we did. We'll practice a couple more. We'll practice more with the transition, 3 examples. And then we'll go on, we'll do polyatomic and practice those a few, and then we'll go on to covalent. So we should really be able to finish the bulk of this by the end of next week. It's so frustrating. I really, and you know what? Tomorrow I won't do this at all. You know that. Like, IT will be sitting here and I'll be like, oh, it's perfect. Look, it's perfect. I just know it. I don't know why. Huh? Yeah, so I tell them, I'm like, look, it freezes. Like my pen will not let me go forward or back. I have to close it and then I have to go back. And then it bumps me off of the LCD projector and I have to tell it to. And they're like,
Do a little video.
that sounds like a lot of compli. And I'm like, yes, it is kind of complicated when I'm up here trying to go, okay, wait a minute. Okay, wait. Okay, it works now. Oh, now it stopped again.
And we